Okay, now we're going to talk about general Bayes theorem. And so first setting this up. So sorry, more mathematics. So we'll let xy to xm be the finite set of m classes in data D. Yq, where q equals 1 to m, is a variable that must be described probabilistically. The feature vector x in D will be an n-component random variable. P of x is the probability density function that x will be observed. P of x given yq will be the conditional probability function for a conditional on yq being its class. And so pyq is the conditional probability that x belongs to class yq. So those are some of the semantics. Here we have some of the equations here, the posterior probability, P of yk given x is calculated from P of x given yq and P of yq using Bayes form. So formula. So here we're using Bayes formula to do this manipulation. So Bayes theorem provides a way to calculate the probabilities of class K based on the prior P y of k and the probability density functions of P of y given yk and P of x given y of k. In terms of the probability mass function, the posteriors can be calculated here. And so this is just building from the equations that we had used previously and introduced. The learner wants to find the most probable case k given the observed x. Any such maximally probable class is called a maximum a priori or MAP or MAP class, which is determined by this equation. And so this is, we've had some mathematical development here for statistical learning, but this is one of those things that is a good takeaway, is having this MAP class determination. So YMAP corresponds to the MAP class provided. So here we have more development of this. And so in many learning scenarios, the learner is interested in finding the most probable class K given the observed data X. Any such maximally probable class is called the maximum a priori class. So that's what we'll be leveraging as we go. Sometimes every class is equally probable with an a priori listed there. In this case, we only consider the term P of x given yq to find the most probable k class. Since Px given yq represents the likelihood of the data x given class yq, and class that maximizes Px given yq is called the maximal likelihood, the ML class. That's why ML corresponds to ML class provided here. So we have the map, and now we have the maximum likelihood types of mathematical developments that we have generated as a result of what we're covering. So let's go ahead and take another short little break. Well, let me cover this first. So for a naive Bayes classifier, the practicability of Bayes theorem lies in the fact that the conditional probability function can be calculated, which can be estimated from data. The naive Bayes classifier uses data-based probability estimation. In typical supervised patterns, which is not what we're focusing on unsupervised. In typical supervised pattern classification problems, each of the P y of q may be estimated simply by counting the frequency which the class yq occurs in the training data. So here we have some more development of the general Bayes theorem. So we have the class conditional probabilities, and then the naive Bayes classifier is based on the assumptions that the given class probability of observing the conjunction is given here. Substituting this, we have the naive Bayes algorithm, where given with this equation, where Y of NB denotes the class output with conditional independence, and the map classifier becomes the NB classifier. So here we're from our alternate source back to Sugiyama. We're just getting an illustration of what the general Bayes theorem could look like and what we're trying to do in terms of the estimation. I think some of the syntax may be a little bit different, but I'm trying to have you focus a little bit more just on the graphical figures that we have. So here we have an example of MLE for the Gaussian model where the number of training samples n is small, and then the MLE tends to overfit the samples, and so we can see what happens as a result of going from one to another. So this is we have a good estimate. This is not working out very well, is the bottom line from that, what I'm trying to draw from that. Okay, let me take another short little break and we'll continue in just a minute.